This is Mrs. O'Neill for AP Chemistry, Chapter 16, Section 9, Acid-Base Properties of Solution. So we're going to explore the fact that ions of a soluble ionic compound can serve as a Bronsted-Lowry acid or base. What do we mean by that? Well, here's an example of a very, very strong acid and a very, very strong base. What does it make? It's a neutralization reaction. So we have a neutral salt and we have that H2O water. So we can always look at it from that KW equation like you've seen before. So in this case, because it's a strong acid and because it's a strong base, you're going to have equal amounts of that H plus and OH minus. However, if you have a weak acid, something's going to happen to the solution because the salt that's being made is also going to be weak, but it's going to be the stronger conjugate base of that weak acid and react with the water to form a more basic solution. So we'll look at some examples and look at an equation, and hopefully we'll get to understand these neutralization reactions. So please write the words, pause the video, and then play to hear my words. But before you do that, before you play the video and hear my words, read over the information. It's a lot of info here this time. So the first bullet you should understand, we talked about ionic compounds and they're strong electrolytes, so they're going to break 100% into ions. So our salt solution that we make, our neutralization salt solution that we make, can be acidic or basic depending on how these ions are going to react with the water in that solution. Okay, so our third bullet here. This should make sense. This is a totally neutral reaction. Strong acid reacts with our base. The conjugate base is so weak, it's not going to react with the water, and that pH stays the same. Or it stays neutral, basically, if you have strong acid, strong base. However, this is where it gets a little complicated. When we have a weak acid and reacting with a base, the conjugate base will actually react with the water, increasing the pH and making the solution basic. Why? Well, remember, if we have a weak acid, that means we have a stronger conjugate base that it forms, and that conjugate base is going to be strong enough to pull those H plus out of the water molecule and make it basic. So again, I'm going to show you some of those, that example then. So this is just a pure example of a neutralization reaction. We have a strong acid, we have a strong base, it forms our salt and water. So that looks like a double replacement reaction. That should make sense. So what's going on here? We have our HA forming our A minus, in other words, our acid removing that H plus, forming our conjugate base. So it stays that way. The H2SO4 is going to break apart totally into ions because it's strong. The NaOH is going to break totally into ions. So we have what's called a very neutral solution. So what do we need to understand? Well, we need to understand that if I'm forming this salt, what acid did it actually come from? So hint, 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 we take that cation away and replace it with our H plus ions. So you get chloric acid. In this case, it's strong. So can you come up with the formula for ammonium sulfate? That would be the salt. And can you come up with the acid? Again, take the cation away, changing it to the H plus, however many you need, to make the compound of the acid it came from. That you should have gotten, and that you should have gotten. Again, another strong sulfuric acid. Now, if HX is weak, if our acid is weak, the conjugate base that is formed will react with the water, push the reaction back to form more hydroxide ions. So here's our weak acid. It's reacting with some base. We form our conjugate base and water. It's a neutralization reaction. Okay, double replacement. Okay. But because our conjugate base now is pretty strong compared to the weak acid, that the strong conjugate base is going to be strong enough to take away those H plus ions from the water, forming more weak acid. And now look at what we're left behind. If this X minus, if this conjugate base is strong enough to take away an H plus, because that's how strong it is, what's going to be left over in our water is OH minus. And this OH minus is going to make this salt solution basic. Okay? So what are the effect of these cations? Well, we have a +1, +2, +2, +3. Notice as we're increasing our cation charge, the pH is actually decreasing. That should make sense. It's decreasing because it's getting more acidic. So if we were to have these salt solutions coming from the acid or wherever it's coming from, maybe a solid just being dissolved, or if it is actually coming from a neutralization reaction, whatever the case may be, as you increase those cation charges, you're going to decrease the pH, increasing the acidity of that salt solution. So let's look at some patterns. Ions that are surrounded by water are called these hydrated metal ions. So the highly charged metal ions will pull those electrons surrounding the water molecules towards them. So the higher the charged ions, it's easier for that H plus to come off of that water. Now it's going to be making it more acidic. So as we're increasing the charge, we're increasing that acid strength. So Mg plus 2 is going to be less acidic than the Al plus 3 because those Al plus 3 has more power to take away the H plus ions, okay, making it more acidic. So here we have a cation has little effect, or I should say, okay, so this cation, which is +1, is very, very weak, okay, so that means that water is going to stay water more. There's not too much attraction here. But when we have this guy +3 and it comes off of the H+, well, that H+ is going to come off, making it more acidic, and we have our pH decreasing, okay, because that +3 has more strength. There's stronger IMF attractions here. Those ion dipole attractions are going to increase, so pulling off that H+, and making the salt solution acidic. So again, the less the charge, the water is going to stay water because there's not as much attraction. It's weak, versus if we have a +3 charge, we have a stronger attraction, and we end up having that H+ coming off. So oxides. An oxide is just a cation attached to an oxide ion. So any positive ion, any positive element, I want to make sure you're understanding that cation has to be a positive element, not a polyatomic. That's what we consider an oxide. So before we go into our notes again, let's think of some questions. So my first question is, if I have a non-metallic oxide in water, so a non-metallic would be any non-metal element with oxygen in water, is that solution going to be acidic or is it going to be basic? Well, let's look at these reactions. Here we have a non-metallic oxide and we're reacting it with water. So if it were to become an acid, our acid would look like this. If it were to become a base, our base would look like this. Now, I don't know about you, but I have seen an acid, H2SO4. I have never seen a base, SOH2, right? I've never seen sulfur hydroxide, but I have seen sulfuric acid. So which one makes more sense? Aha! So again, I'm trying to get you to understand that you can look at a pattern instead of memorizing, but we will put in your notes that a non-metallic oxide reacting with water would become more acidic. Now let's look at metallic oxides. Again, a metal element with oxygen in water, is that going to produce an acidic or basic solution? Well, again, I'm asking you those same questions. What would be the acid that would come from this? What would be the base that would come from this? So I don't know about you, but I couldn't even name that acid because I have no idea what that is, but I can name this base, calcium hydroxide. So which one makes sense? The base. So we want to remember that oxides in water, a non-metallic oxide dissolved in water is going to be more acidic because it's going to come from this and this. So there you have your two acids from the non-metallic oxide it comes from. So think about that soda as well. This carbonic acid, you know, kind of breaks apart always into carbon dioxide and water. That's why soda is on the acidic side, is because it comes from that acid. And metal oxides dissolving in water produce that base, in this case KOH. So hopefully that makes sense now going through those questions. Also, you can think about that periodic table. Remember that strong bases are on the metal side. So a metallic oxide is going to make a base, and a non-metallic oxide is going to make an acid because they're on the non-metal side. So give it some thought, see if you can come up with an answer. Hopefully that makes sense and you had some kind of formulated answer similar to this. See you in class.